This section is on the properties of logarithms, and also we're going to talk at the end about changing bases of logarithms. Now remember, in the definition we said the log a of x was the exponent of a that gives you x. So when you see the word log, you can think exponent. And so it's not surprising that the properties of logs would come from the corresponding properties of exponents. I listed the exponent properties from algebra over here on the right. First one is x to the a times x to the b is x to the a plus b. So what you can say is, if you take a product, the exponent of that product is the sum of the exponents. Okay, a plus b is the sum of a and b. So our first log property says the log of a product is the sum of a logs. If you just replace the word log with exponent, it says the exponent of a product is the sum of the exponents. So it's really the same property. I've written it here. Here's the log base a of the product uv is the sum of the logs, the log base a of u plus the log base a of v. If you look at the second exponent property, it's talking about the log of a quotient. We have here the quotient of x to the a over x to the b, and the exponent of that quotient is the difference of the logs. So I'll say the log of a quotient is the difference of the logs. So here's the log of a quotient, log base a of the quotient u over v, and that's supposed to be the difference of the logs, so I'd say the log base a of the upper number minus the log base a of the lower number of the quotient. The last one's a tad more complicated. It shows you how to take the log when you exponentiate an exponential, and it says the exponent of that exponential is the exponent times the exponent. So in our case, we want to take the log of an exponential, log a of u to the n, and we want it to be the exponent times the exponent. Well, n is an exponent, so there's an exponent, and log means the exponent, so there's another exponent, so we get the exponent times the exponent. So we say the log of an exponential is the exponent times the log. Now you need to know these: the log of a product, the log of a quotient, the log of an exponential. Now, these things I gave you are not proofs. They're just kind of memory devices to think of basic properties of logs in the same way that you think of basic properties of exponents. I'll go ahead and do a proof here of the third one, just so you can see that they can be proved. And this one says the exponent of a that gives you u to the n is n times the exponent of a that gives you u, or n times the log a of u. Now this n log a of u is supposed to be the exponent of a that gives you u to the n. So let's make it the exponent of a, and let's see if we really do get u to the n. Well, that exponent is a product, n times log a of u. Now I want to emphasize here, this thing log a of u is a single number. That's not three numbers, it's a single number. It's like function notation. If you didn't have the u there, it would be like having f of and then saying what you don't have f of, or not saying what you do have f of. So you need all of this together to be a single number. So it's n times this number, and since multiplication is commutative, that's the same as the number log a of u times n. And if you look at your last rule of exponents, x to the ab is the same as x to the a to the b power. So I could call this log a to the log a of u to the n. Now think of what this expression says. This is a to the exponent of a that gives you u. Well, if you put a to the exponent of a that gives you u, you get u. So that's u to the n. And we have shown that n log a of u is the exponent you put on a to get u to the n, and that proves the third property. Now, once you've got those properties, well, what do you do with them? Well, there's two main uses. If you look at my first example here, you have a log of something that's really complicated looking. We can use those properties to write these in terms of simple logs, sums and differences. So let's get started. It says the log 4 of a quotient. Well, we go to our quotient rule. The log of a quotient is the difference of the logs. So I write this as log 4 of the upper number, which was x plus 3 times. And now, see this square root of 4 minus x? Recall that the square root of a number is the number to the half. So I'm going to change this to 4 minus x to the half. And it's the difference of the log, so it's the log of the upper minus the log of the lower, so that would be log 4 of x cubed. Now I've got the log of a product. Well, according to the first rule, the log of a product is the sum of the logs. So I'll write that as log 4 of x plus 3 times log 4 of 4 minus x to the half. And on this second log, that's the log of an exponential. That's the third rule. So that's the exponent times the log. So I'll write it minus 3 log 4 of x, and I've broken that down to a very simple log there. Well now, and this was a sum of the logs. So we needed a plus sign here. Well, now this second term is the same thing I had with the third term. It's now the log of an exponential, so I'll bring that 1/2 out front. So I'll have the log 4 of x plus 3 plus the log 4, plus 1/2 the log 4 of 4 minus x minus 3 log 4 of x, and I have broken that down into a sum of simple logs of one item. Now you might say, well, can't you break down the log of 4 minus x? Well, that would be the log of a difference. Do you have a rule on the log of a difference? You have the log of a product, the log of a quotient, the log of an exponential, no log of a difference, so this problem is done. Now, suppose I gave you the opposite problem. I gave you a sum of logs and I wanted you to write it as a single log. Well, just reverse the steps. This would be your first step. Move up to here for your second step. Get the 3 out, get the half out, make them exponents again. Take the sum and change it to a product. And then finally take the difference, change it to a quotient. And you've taken this big long expression here and you've written it as the log of a single item. Now the last thing I wanted to talk to you about was changing bases. If I gave you a problem like this, evaluate log 5.6 of 29.3, that's a handful. You're trying to find the exponent of 5.6 that will give you 29.3. Man, that would take a long time. But you can do it in a jiffy with something called a change of base formula. The reason this is hard is because the log 5.6 isn't in your calculator. But you can change that base to something that is in your calculator, and here's the rule. If you have the log to any base, like I'm just calling it here base A, and you want to change it to any other base, which over here I call base B. Notice x is the upper number, A is the lower. Just take log B of the upper over log B of the lower. And you have changed from the log A to the log B. Now you have a quotient in log B, but that's okay. All you have to do is hit divided by in your calculator. So let's see how this one would work. Clearly I don't have log 5.6. The only logs I have on my calculator are ln, which is the log base E, and log, which is the log base 10. So suppose I wanted to change it to log. Then I could just write that the log 5.6 of 29.3 is equal to the log of the upper 29.3 over the log of the lower 5.6, and I have put it into something that is in my calculator. Now when I actually put that in my calculator, I get a big long number that starts off 1.96 and it goes on and on and on and on. And if I wanted to check to see that I really got the log of 5.6 that would give me 29.3, I would just put into my calculator 5.6 to the power and hit the answer key. And that would give me all those decimals, and when I did that I'd get 29.3. One last thing. If I ask you to graph log 2 of x, log 2 is not in your calculator. So change it to log of x over log of 2, And that's something that is in your calculator that you can graph, and that ends the podcast.